So imagine we have a generating station in which we are generating electricity at 11 kilovolts, and then we are transmitting it by stepping it up to, let's say, 400 kilovolts to a long distance. And when we get that electricity at the receiving end, we see that the electricity, the supply voltage that we are getting is not 400 volt, but let's say it's 510 kilovolts. So you see there is significant difference between the voltage that we are sending and the voltage that we are getting, right? And this is really happens. I mean, this is the actual fact. This is the actual scenario in the transmission line in the power system. And this is what we refer to as the Ferranti effect. Let me actually show it to you using a circuit simulation. So here we have a simple generating station, a voltage is set, and this is the equivalent circuit of the transmission line. It's a long distance transmission line. And you see this is our load, which is currently disconnected. So what I will do, I will close the circuit so that the load is connected to the system. And now I'm going to run the simulation. So you can see this green dot or the green waveform represents the voltage at the sending end, which is at 353 kilovolts. And the purple dot or the waveform indicates the voltage at the receiving end at the load side, which is showing as 356 kilovolt, which is okay. The difference between these two is not very high, and this is acceptable, perfectly fine. But now see what happens. Now I'm going to disconnect the load from the transmission line, and then you see what happens. You see there is a sudden spike in the voltage. There is a sudden spike in the voltage, and now let us look at the RMS value. So you see sending end voltage is still the 353 kilovolts, no change of course, but the receiving end voltage has gone up to 522 kilovolts, which is huge. So there is a significant gap between the voltage that we are sending and the voltage that we are receiving. And this effect in the transmission line or in the power system is referred to as the Ferranti effect. In this video, we are going to break down this, and we are going to understand why the voltage at the receiving end is so high when there is no load or it's light load. We'll break down everything in this video. So let us go and understand that. So here we have the transmission lines. Now transmission line is what is nothing but a long conductive conductor which is carrying electricity over a long distance. So for sure, no doubt, because no conductor is 100% pure. So here also we will have some impurities, and impurities in electrical circuit is what? Resistance, inductance and capacitance, right? So there will be definitely resistance present in the transmission line, correct? And since this transmission line is carrying the alternating current, of course, there will be inductance present in the transmission line, no doubt about that. Right? So we have R, we have L in the transmission line. Now, if you focus on this transmission line, for example, these two lines that you see here, this one and this one, both of these lines are carrying current, right? No doubt about that. And between these two conductors are basically insulated with the help of air, right? And what is this? This is basically a capacitor. Why? Because we have two conductors which is carrying current, and they are also insulated by some sort of insulating medium. And this is going to act as a capacitor. And this is not only between the transmission line, but also between the transmission line and the ground. The capacitance value will be there. The capacitance will be there. So undoubtedly, we will also have a capacitance which is in parallel, by the way, not in the series. So the problem is we do not have any issue with the resistance. Even if it is present there, it's not going to cause a lot of problem to us. Okay. The problem starts when we have inductor and capacitor in the system. Now what happens? Let us go and understand that. So let's take a quick example of two transmission line which you can see on your screen. So I've drawn an equivalent circuit now, and this circuit is just for understanding purpose. So imagine these are the two transmission lines and which are loaded fully. Okay, so there is load connected to this transmission line. Okay, now what happens when there is a load? Of course, the current will flow through the transmission line, no doubt about that. When the current flows, through this transmission line, the current has to go through the resistance, it has to go through the inductance and also the capacitance. Now resistance I have not shown here for clarity purpose. So when current passes through the inductor, of course there will be voltage drop happening here, right? Because of the inductive property, it's going to generate the EMF and there will be voltage drop across that. Similarly, the current will also flow through the capacitance that is getting generated here. So here there will be voltage, right? Because capacitors are capable of storing the charge, right? So for sure there will be voltage rise. So this inductor and the capacitance are exactly opposite to each other. And what happens is when the line is completely loaded, they cancel out each other. So the effect of capacitance and the effect of inductance is cancelling out each other. And that's why you see when we saw the simulation, the sending end and the receiving end voltage was almost equal, right? When the line was completely loaded. And when this is the scenario, we do not have any problem. We are absolutely okay with this. But the problem start when the load is disconnected. Okay, now we have removed the load. Now let's see what happens. Now, of course, load is not there or transmission line is very lightly loaded. Now, in this scenario, still there will be some current flowing to satisfy the requirement of these capacitors here. And the current will flow through this, and this is called as the charging current. Current will flow through this capacitor. It will not be very high, it will be minimal, but definitely the current will flow. And because the current is flowing through these capacitors, the capacitors will charge, so there will be voltage rise happening here. But the problem is, since the current is not high enough, the inductance, the voltage drop that should be happening here is not happening, right? And as a result, what you will see, all this voltage rise adds up, and in the end we get additional voltage. Because when there is no current or there is no load or the transmission line is lightly loaded, the capacitive effects dominates over the inductive effect. And as a result, in the receiving end, the voltage that we get is actually very high compared to the voltage that we are sending. Please remember, understand this basic. Why this is happening? Because the effect of inductance has gone down in the system and the effect of capacitance dominates the system. That's why there is a voltage rise at the end of the transmission line. And this is a problem because if I'm expecting voltage to be at, let's say, 400 kilovolts, but I'm getting 550 kilovolts, just a random number I'm taking for understanding. This is a problem, right? Because my equipments are not meant for 550 kilovolts, they are meant for 400 kilovolts. And if this voltage stays in the system for a long time, of course, there will be problem over voltage. And this is something we must avoid. So how do we tackle this issue? Well, what has caused this issue? Number one, because the inductive effect has gone down, and that is the result, the capacitive nature of the transmission line is dominating. So it is very simple. We introduce a inductance in the system. And how do we do that? Of course, with the help of a reactor. So a reactor that you see in the system is basically a huge inductance that we add. Now, when we add that, it basically, exactly opposite to the capacitive impact, and they cancel out each other, and in the end the voltage is stabilized. So a reactor is a very, very important component of the power system. Now, if you want me to make a dedicated video talking about what is this reactor and how it compensate this Ferranti effect, then definitely comment reactor in the comment section. If I get enough comments, for sure I'll be making a video on that. But I hope you understood the basic. The problem is when there is full load, we do not have any problem because the current will flow in the system and the inductive effect and the capacitive effect will cancel out each other, will receive the similar voltage. But when the supply, when the load is not there or the transmission line is lightly loaded, the inductive effect is not present because there is no enough current flowing through that inductor to give us that inductive effect. But certainly there will be small amount of current which will flow through the capacitance, and that will generate the voltage, and everything will be added up, and in the end we will get a very high voltage at the receiving end. Now it's very important to understand this Ferranti effect you may not find in the transmission lines which are 50 kilometers or 100 kilometers spreaded in the system. This is more prominent when the transmission line length is more than 200 kilometers. So 200 kilometers, 300 kilometers, these are the transmission line which are very much exposed to this effect, and that's why you will find generally in 400 kV systems or 800 kV system where the transmission length is very high, reactors are used. Generally below 245 kV the reactors are not used. And this effect increases when we have cables. Now why this is because in the cable the two conductors, the distance between the two conductor is small because we are using some physical insulation there, and that's why in the cable side this effect is very, very high compared to the overhead transmission line. Clear? So I hope you understood what is this Ferranti effect, what is the cause of that, because understanding the cause is really, really important, because that is going to clear all your basics. Well, there is another interesting effect that happens in the transmission line, and it's referred to as the skin effect. I have talked about what is the skin effect in one of the dedicated video. If you are interested in watching that, I'll put link for it down in the description and other relevant videos. So definitely go and check it out to know more about that. Thank you so much for watching, guys, and I'll see you in my next one. But till then, keep watching, keep learning.